So good afternoon, Causeway. It's a pleasure to be here once again to talk to you. So this is keeping an eye on the universe, what telescopes tell us about how the universe works. So we know that 400 or so years ago, Galileo pointed his telescope skyward and recorded phenomena such as the changing phases of Venus and the movement of the moons of Jupiter. Since then, telescopes have moved on. Instead of using lenses, they started using mirrors. And in the last 100 years or so, we've seen large telescopes such as the Hooker telescope with a mirror 2.5 meters in diameter, and the Hale telescope with a mirror 5 meters in diameter. And telescopes like these allowed Edwin Hubble to look out into the universe to deduce that galaxies were moving away from us, receding from us, and hence we're living in a universe which is expanding. That helped us get an idea of the universe in which we live, its history, and indeed its future. And of course, now we live in an era where we have space telescopes, such as the Hubble Space Telescope, which has been with us for more than 3 decades now, and the new kid on the block, the James Webb Space Telescope, launched in December of 2021. But in addition to these, we have other major telescopes coming online in the near future. For instance, it won't be too long before we see the European Extremely Large Telescope, so named because its mirror is a whopping 40 meters in diameter, much larger than any telescope up to this point. And I'll be saying a little bit about those telescopes in a few slides' time. This is a useful way of just getting an idea of the scale of all of these telescopes. So this isn't every telescope in existence, it's only the larger ones with mirrors substantially larger than a meter or two. And the largest of these at the moment, the largest operational telescope, is the Gran Telescopio Canarias. We talk about diameters, but of course if it's made of hexagonal segments then it really hasn't got a diameter as such, but roughly speaking it has equivalent diameter of about 10 meters or so. And although that's the largest at the moment, it won't be too long before much larger telescopes come online, as you can see from the right hand side of this diagram. But what's of interest to us at the moment is other telescopes such as the Hubble and the James Webb, and they are in the bottom left of this particular diagram. Notice that space telescopes have mirrors that are substantially smaller than the telescopes of today and very much smaller than the telescopes of tomorrow, in the sense that even the James Webb, which is substantially larger in terms of its mirror size than the Hubble Space Telescope, that is only 6 meters across rather than the 10 meters of the Gran Telescopio Canarias. And that's simply because of the difficulties of obtaining telescopes that can be small enough to be launched in rockets either into Earth orbit or, in the case of the James Webb, well away from the Earth's orbit at a location which we'll come to shortly, called the L2 point. So we can see that telescopes have continually got larger and larger with time, from centimetre size in Galileo's day to metre size now, and it won't be long before we're talking about tens of meters in diameter. And this drive is always about collecting more light and also giving us more resolution, more fine detail of the objects that we want to observe. So this must be an iconic telescope. There can't be many people who look at this and don't recognize what it is. You don't have to be an astronomer. I would argue you don't even have to be a scientist to recognize what this is, even if you don't fully appreciate what it's done for science, what it's done for astronomy. It's been in operational now for more than 30 years, since its launch in 1990. And it's given us spectacular views of the universe, not least the deep field images where it pointed at what was thought to be perhaps a blank patch of sky, exposed for as long as is feasible, turned out to be about 1 million seconds or about 11-12 days. And then it realized that the universe is not empty. Even though this was a blank patch of sky, it's revealed thousands upon thousands of galaxies. So there might be one or two stars in this image which happen to be in our own Milky Way, but pretty much everything else is more distant galaxies. And that gave us a handle on just how big the universe is, and the fact that it's full of at least 1 trillion or so galaxies, in the sense that we can observe about 1 trillion within our sphere of observation. We can only see a finite part of the universe. We don't know what is outside the observable universe, but within that sphere that we can see, there are some trillion or so galaxies. And to remind ourselves what a small patch of sky that was, the Hubble Deep Field, indeed virtually all of Hubble's images, are shown by that red rectangle to the same scale as how big the moon would appear in our sky. You can see that the area of sky covered by a Hubble Space Telescope image is only a tiny fraction of the equivalent of a full moon. And remember, the full moon is about 1/2 a degree in diameter and is itself only a tiny fraction of the whole sky. We'll come back to this image later when we think about the scale of other telescopes. And just to prove it wasn't a fluke, if we look in one particular direction and we see in our field of view thousands of galaxies, just to show that it's not a fluke and we happen to be looking in a direction in which there were lots of galaxies and perhaps there aren't many in other directions, the Hubble was then instructed to take another deep field image in a different part of the sky, looking in almost the opposite direction, and it revealed essentially the same thing. Of course, different galaxies, but with the same distribution of some galaxies close to us, some galaxies in the distant, and some galaxies very remote from our location, many, many billions of light years away. So the Hubble Space Telescope was very good at giving us a sense of perspective. But in addition, it gave us close-up views of some of our nearest neighbours, not perhaps the most remote galaxies, but the ones that are a little closer. The Hubble managed to produce exquisite detail to give us much better idea of how galaxies evolve and how they came to be. Of course, any image like this is just a snapshot, and we would need to take images of lots of galaxies to get an idea of how galaxies evolve. This particular galaxy, rather beautiful, has got a very large bar across the centre. You can see the centre of the galaxy has this large bar down the middle, and then the spiral arms seem to originate from the ends of this bar. It's thought that the Milky Way is perhaps a barred spiral, but not quite as distinct as the bar that we see in this particular example. The more we look in terms of different galaxies that are out there, the more we realise that galaxies, generally speaking, are not in isolation. A lot of galaxies are interacting with their neighbours. This is simply because the average distance between galaxies is a lot less than, for instance, relatively speaking, the average distance between stars. The size of a star compared to its distance to its neighbours is very small compared to the size of a galaxy compared to the distance of its neighbours. So it's not surprising that a lot of galaxies will interact with their neighbours. And here we see a lovely example of two galaxies. They may have started out as spiral galaxies, but the gravitational pull of one on the other has distorted both of them into these rather interesting shapes. And whenever we look at galaxy interactions and galaxy collisions and galaxy mergers, we realise that whenever two galaxies collide with each other, it might sound rather apocalyptic, but actually when two galaxies pass through each other, no two stars are particularly likely to collide with each other. It is likely that galaxies pass through each other and all of the gas and all of the dust does interact, and that gives rise to a riot of new star formation, which is indicated by pink in this particular image of two galaxies colliding. And the new star formation means that this is by no means the death of a galaxy. If anything, it's a sort of rebirth. The two galaxies will end up merging together, the galaxy will end up larger, and new stars will be born as a result of the interaction. When we look at what's going on inside our own Milky Way, the Hubble Space Telescope has been able to look at objects such as these, so-called planetary nebulae. Nothing to do with planets as such. This is the death of a star much like our Sun. In the future, when our Sun runs out of nuclear fuel, it will expand to a red giant and eventually slough off. The outer atmosphere, the outer layers of the Sun, will end up getting expelled into the interstellar medium and form a nebula such as this. This is the Helix Nebula in the constellation of Aquarius, seen rather low down in the south, as seen from the United Kingdom. So in a sense, this is what we have in store. Whether the Earth still exists in billions of years to come, when the Sun eventually goes through its red giant phase and ends up as a nebula similar to this one, well, we don't know whether the Earth will be around, but this is what is in store for the Sun. The core of the star that sloughed off its outer atmosphere is this very small star in the middle here. The star, after it's gone through the red giant phase, what's left of the core of the star will end up being what we call a white dwarf. And that's what our Sun will become in another 10 billion years or so. If the star is more massive, it could end its life not by generating a planetary nebula, by slowly kicking off the outer atmosphere of the star, but it could, if it's massive enough, end its life as a supernova. And then it's a rather more dramatic and violent affair, which will effectively blow the star to pieces and redistribute essentially all of the material of the star into the interstellar medium, as this particular supernova remnant indicates. This is the Crab Nebula. This particular supernova was seen in 1054 and has been expanding for the last 1,000 years as we observe it. I'm not showing it here, but the Hubble Space Telescope has taken images of the Crab Nebula a few years apart and has shown that yes, it is expanding ever so slightly each year. Another rather nice supernova remnant is called the Veil Nebula. The inset there in the top left shows the entire nebula in its entirety, about 3 degrees or so in diameter, much larger than the diameter of the full moon, though of course rather fainter. And in this particular case, because the Hubble can't image the whole thing because it's simply too large, the Hubble has imaged what's in that little red rectangle shown in the inset. So this is a tiny part of the whole of the supernova remnant, and it's looking at effectively one of the shock waves that's been produced by the supernova. The material that's been thrown off from this supernova is ploughing its way through the interstellar medium, and as it does so, the material being thrown off is interacting with the interstellar medium, and we see all of these beautiful colours that are the result of different atoms glowing with different colours. In there are atoms of hydrogen and sulfur and oxygen, and no doubt many other elements as well, and each element gives off characteristic coloured light, and that's what's being picked up in this image, and then the colours are combined to give you this beautiful colour image. But it reminds us of the complexity of something like a supernova remnant. Trying to understand the structure of what's going on in there helps us understand not only supernovae, but also helps us understand the nature of the material that exists between the stars. Gravitational lensing is something I've mentioned before, but in this particular case, I think this is one that's worth pointing out again. When I gave you a talk some time ago about the Hubble Space Telescope, I pointed to this as being one of the crowning achievements of the Hubble, in my opinion. It imaged a very distant galaxy where the light from the distant galaxy has been bent by a whole load of galaxies in between us and this rather distant galaxy. So this one that we can see here in the white box is rather distant, but in between us and this galaxy are these other ones that look a little bit orange in this collection of galaxies, a supercluster of galaxies. These are somewhere in between us and the more remote galaxy. And the light from this galaxy has been bent as it passes this very massive supercluster of galaxies in a process called gravitational lensing. The light is bent in a similar sort of way to the way light bends as it travels through a glass lens. But here the lens is imperfect, And the light from the distant galaxy, shown zoomed in this inset here, we see in this distant galaxy 4 yellow dots, and we interpret this as being 4 supernovae. But there can't possibly be 4 supernovae all going off at the same time. That seems very unlikely. A supernova might be expected to go off perhaps once every 100 years or so. So getting 4 going off at the same time seems ridiculously remote. And this is interpreted as being a single supernova that's being imaged 4 times. The light coming from the supernova to us is taking different paths as it is being bent as the light travels through this region of very high mass because of this very massive supercluster of galaxies. And the light takes 4 different routes, and we end up with 4 images of the same object. It's like having extreme magnification through this particular phenomena that was predicted by Einstein, and Hubble and indeed other telescopes have been able to prove indeed that light does get bent by massive objects, space gets distorted, space gets warped by massive objects, and as a consequence light takes different paths to reach us from more distant objects. So a rather remarkable set of images from Hubble there. And of course the iconic images that we all remember, especially the more visually appealing ones, are images such as this one, Mystic Mountain, which is part of a much bigger nebula visible in the southern hemisphere called the Eta Carinae Nebula. And the pillars of dust that we see here are sculpted by the stellar winds from various hot stars, some of which are embedded and invisible inside the pillars themselves. We can see some stars in this image, but optically it is very dusty environment and very difficult in the optical to see what's going on inside these pillars sculpted by stellar winds. But as well as Mystic Mountain in the southern hemisphere, we have of course the Pillars of Creation, which is visible from the northern hemisphere, still south of the equator, but visible from the northern hemisphere in the Eagle Nebula. We have the famous Pillars of Creation, imaged by Hubble soon after it was launched and then re-imaged for its 25th birthday to show the wonderful instrumentation, some of which had been swapped out during the years of its service. This is one of the reasons that Hubble has been so successful, is because it was possible to be serviced by astronauts who could change the cameras and the spectrographs and continue to update the hardware with the latest developments as the decades moved on from the 1990s to the noughties. And of course no longer possible as we no longer have a shuttle fleet to service the Hubble Space Telescope. But the new kid on the block is the James Webb Space Telescope. Not a replacement for Hubble. Hubble is still doing well. James Webb should be seen more as a complement to the Hubble Space Telescope. Yes, it has some more interesting technology aboard, but it is not trying to do the same things as Hubble. The James Webb Space Telescope is working principally in the infrared. The Hubble Space Telescope worked principally in the visible part of the spectrum and a little bit in the infrared. James Webb is the other way round, a little bit in the optical part of the spectrum, but mainly in the infrared. So a little bit of overlap between the two, but essentially they are covering different parts of the electromagnetic spectrum, and hence they are doing different things, looking at different objects, and coming to perhaps different conclusions about understanding those objects. So the James Webb, it's been a long time coming. It took a long time to build it. It took a while to fold it up, as indicated by the middle image, and then check it unfolded correctly here on Earth, before its final folding up and then placing on top of a rocket and being launched in December of 2021. Now, it's a lot larger than the Hubble in the sense of its main mirror. We can see the hexagonal segments of the James Webb Space Telescope in the middle there, with a nominal diameter of more than 6 meters, compared to the 2.5 meters or so of the Hubble primary mirror shown on the left. So that means, amongst other things, it can catch a great deal more light simply because its larger surface area. In principle, it might mean that it would be able to resolve more detail simply because it's a larger mirror, and usually larger mirrors mean more detail. But remember that the James Webb is working in the infrared, which has a longer wavelength than the optical, and the actual resolution of a telescope is determined by the size of the mirror compared to the wavelength that it's operating in. So James Webb, larger mirror but longer wavelengths, means a lot of the time it will have a similar spatial resolution, its ability to resolve fine detail. It'll be comparable to the resolution possible from the Hubble Space Telescope. But the James Webb is not placed in orbit like the Hubble. The Hubble is in orbit around the Earth at a height of a few hundred kilometres or so, but James Webb is somewhere altogether different. There are 5 points indicated by these red dots that are called Lagrange points. These are sort of parking places that you can put a telescope. And the one shown on the right there, called L2, that's where the James Webb has been parked. It is sitting there, if you remember that there's the Earth and of course the face of the Earth facing the Sun. That's where local noon would be, where my cursor is. And on this side, the point away from the Sun, is local midnight. And therefore L2 is this parking place which is sitting approximately 1 million miles above midnight. So that's why you get that particular phrase used occasionally. All of these red points, Lagrange points 1, 2, 3, 4, 5, all move at the same rate as the Earth. In other words, they all go round the Sun in 1 year because of the way gravity works. That's a subject of a different talk. So L2 is actually the parking place for more than just the James Webb. It's actually where Gaia is parked as well. Strictly speaking, not at the L2 point itself, but in an orbit around L2, because that is easier for the control of the spacecraft and positioning and station keeping the spacecraft at that particular location. It also keeps the spacecraft out of the Earth's shadow. The advantage of going to L2 compared to Hubble staying in Earth orbit is that if you have a spacecraft here at L2, then with a single sun shield, as indicated here on the right by these tennis court-sized sheets of mylar, then with a sun shield you can block the light from the Moon and the Earth and the Sun because they're all in the same direction as seen from this point L2. So you don't need to have multiple shields keeping the heat of the Moon and the Earth and the Sun away from your sensitive electronics. Remember, the James Webb is working in the infrared, and so all of its instruments must be cold, because if they were warm, they would be radiating infrared light themselves. So the mirror and all of the detectors and all of the electronics have to be kept nice and cold to make sure that the James Webb works as it should. And by placing it at L2, the sun shield is able to make sure that happens. So one of the things James Webb is going to be doing is looking back in time. If we think about the length of time the universe has existed, from the Big Bang on the left, 2 billion years, 4 billion years, 10 billion, 12, 13.8 billion years after the Big Bang, that's where we are now. And it's possible to look back in time, not just the James Webb, any telescope can look back in time, simply by looking for more distant objects. And the distance to these objects is indicated by the quantity that we can measure, which is called the redshift, here indicated in red by the number Z. This simply indicates by how much has the light been stretched. Remember, we live in an expanding universe, and the more distant an object is, the longer it's taken for the light to reach us, and the more of the universe it's had to move through, and remember, the universe is expanding. So as the light takes time to be emitted by this distant object and arrive here on Earth, the light is getting stretched, its wavelength is getting longer by an amount that depends on how far it's travelled, how far back in time we are looking. So if we see an object that's had its wavelength stretched by a Z of 1, meaning its wavelength is effectively twice as long as it was when it left the object, that corresponds to an object that emitted the light some 5 billion years after the Big Bang, or a little less than 10 billion years ago. And if we can see more distant objects, we will find that their light has been stretched even more. For instance, if we went to a Z of 4, we would be going back to this point 1 or 2 billion years after the Big Bang. And one of the reasons that the James Webb Space Telescope exists is because we want to go as far back in time as possible. We think a lot of interesting things happened in this first 1 billion years. In particular, we think that that period was when the first stars and the first galaxies were born. So we can see early-ish galaxies, meaning galaxies more than 10 billion years old, but can we see back to the very first stars and the very first galaxies? If we blow that little time period up there a little larger so we can see it more clearly, we think that stars and galaxies were born in these first few 100 million years, this fraction of a billion years. But we don't know exactly where or when. Were they born 100 or 200 million years after the Big Bang, or did we have to wait until 3 or 4 or 500 million years after the Big Bang? The Hubble has been looking at distant objects back to approximately a redshift of 10. That means light has been stretched some 10 times longer than the wavelengths when it left the object. And so the Hubble is able to look back to galaxies that existed some 500 million years after the Big Bang. But the intention is that James Webb Space Telescope, because it's working in the infrared, remember that light is being stretched, and if light starts off in the ultraviolet or visible part of the spectrum and gets stretched by a factor of 10 or 20, then it's no longer in the visible part of the spectrum, it's now in the infrared part of the spectrum. And that's why the James Webb is looking, that's one of the reasons it's looking in that part of the spectrum, because it's hoped to be able to see faint galaxies at much larger redshifts. And in particular, it should be able to go beyond Z of 10 and hopefully to a Z of 14 or a Z of 20 or perhaps one day even a Z of 30. Very distant galaxies from very early times in the universe have had their light stretched, and maybe the James Webb will be able to see that and push us back to asking what happened in those first 100, 150, 200 million years after the Big Bang. If we still see stars and galaxies even going back that far, that means stars and galaxies must have formed rather earlier than we first appreciated. So it tells us something rather fundamental about how the universe came to look the way it does now. Perhaps this process started earlier than we thought. That's one of the key observations that we hope James Webb will be able to help us with. So the first light of the James Webb came about halfway through 2022, where various images were released. I'm not going to talk in detail about all of these, but we got the cosmic cliffs showing a star formation in the Eta Carinae Nebula. It showed us planetary nebula, which were seen in more detail because of its ability to look in the infrared and deduce what's going on with the central star in this planetary nebula. It showed us interacting galaxies. Admittedly, these were already imaged by the Hubble Space Telescope, but by looking in the infrared, we got more information about how these galaxies are interacting with each other. In the top left, we see again a galaxy cluster distorting the light from more distant galaxies. These little arcs that we can see are simply galaxies in the distance getting distorted by passing close by these supermassive galaxies in the foreground. Again, gravitational lensing. We've seen that with the Hubble Space Telescope. The James Webb will be looking at more examples of this to give us more information about the most distant galaxies. But as well as imaging, the James Webb will be able to take spectra, and one of its jobs is to look at the spectrum produced by distant exoplanets, different planets going around distant stars, with the hope of being able to identify the chemistry of what's in the atmosphere of these very distant exoplanets. And so far, the James Webb has been able to identify water, as well as sulfur dioxide, as well as carbon dioxide, as well as various other molecules. It hasn't yet found any signs that are definitive signatures of life on these other planets, but maybe that will come before too long. By studying the Tarantula Nebula, this is a star-forming region in the Large Magellanic Cloud. This is quite distant, but it is a very interesting cloud to examine with the sort of detail that the James Webb can bring to bear on a region like this, because it's able not simply to take a pretty picture showing the structure of this nebula, it's able to image at different infrared wavelengths because of its spectroscopes and cameras. And so it's able to image in fine detail. Here's the full image, and then we're blowing up a region around a star, and then we're blowing it up again. And now we can see the star looks different in different colors of infrared radiation. So we can use an infrared wavelength that tells us what atomic hydrogen is doing, the blue, and we can use an infrared wavelength a little bit longer that's telling what molecular hydrogen is doing, 2 atoms of hydrogen bonded together. And using longer wavelengths again, we can see what dust is visible in this system. And amongst other things, this is telling us that if you notice there's not much blue around the star itself, there's a lot more green in the neighborhood of this apparent bubble that seems to be excluding atomic hydrogen but including molecular hydrogen. So who cares whether hydrogen is 1 atom or 2 atoms making a molecule? Well, that matters to star formation because we believe that we need molecular hydrogen to start the process of forming stars. Stars find it difficult to be made out of simply atomic hydrogen. Usually there's too much energy, whereas molecular hydrogen is a little bit colder and it's a little bit easier to condense gravitationally to form a star. So understanding the difference between atomic hydrogen and molecular hydrogen is very important for our understanding of the basics of star formation. And the James Webb is helping us in that process. We know that the Hubble Space Telescope imaged the pillars of creation, so it was no surprise that the James Webb went back to this target to produce this wonderful image in which we're no longer obscured by the dust and gas of these pillars. We can now start to see inside them. And we have so many more stars visible in this image because in the infrared we're not so sensitive to the dust, and we can start to see inside the pillars and again get a better understanding of the formation of new young stars. That's effectively just the same image, but processed a different way with a different colour palette, which simply brings out this sort of spooky, released for Halloween in 2022 sort of image, but I think it's still a very dramatic image. This I quite like as one of the early targets that the James Webb Space Telescope went for and released in October of 2022. This is an interacting galaxy or pair of merging galaxies. Remember, this is not necessarily cataclysmic. It's a perfectly natural way for galaxies to evolve. We think merging of galaxies, coalescing of galaxies, is part of the evolutionary process. Large galaxies tend to eat smaller galaxies, and sometimes 2 galaxies of a similar mass will merge together. In this particular case, this is a pair of galaxies that's imaged by the James Webb, which again was also imaged previously by the Hubble Space Telescope. And I think a comparison of the two makes it very interesting. This one is the James Webb, and I will flick forward to the same image with the Hubble. There it is. And I will just oscillate backwards and forwards, and the initials in the top right tell you which one we're looking at. But if we go backwards and forwards and look at, for instance, some of the detail in the galaxy, notice that the resolution, the smallest object that we can see in this particular pair of images, is pretty much the same for the James Webb and the Hubble. Remember what I said, the James Webb has a larger mirror, but the James Webb is operating at longer wavelengths, so the resolution ends up being very similar. But notice that some of these more distant galaxies look a lot brighter for the James Webb than they do for the Hubble. There's the Hubble, there's the James Webb. So these distant galaxies, which are probably so remote their light has been stretched from the visible to the infrared, then these galaxies are brighter in the infrared and hence they show up more clearly in the James Webb image. But the other thing to note is that what's going on in the center of the image, here the image is obscured by an awful lot of dust and the Hubble is having difficulty seeing what's going on in there, whereas the James Webb clearly shows there's a very bright object at the core of these two. This is probably the birth of these two galaxies colliding and perhaps feeding matter into a supermassive black hole right at the center of this galaxy. Difficult to see when it's so dusty, difficult to see in the visible, but it starts to show more clearly in the infrared. And there's another example of the synergy between the Hubble and the James Webb. They don't see the same things, even looking at the same object. This particular image I like just because it's a beautiful image. This is the birth of a star, or at least the birth of a solar system around a star. So here we have a great deal of matter being sucked in to the region right at the center here. So we have a lot of dust. It's a little bit thinner at the bottom than it is at the top. So there's a slight difference in the coloring here. The colors are the result of taking images at different infrared wavelengths. But the material from this large cloud of hydrogen is forming something you can't really see right at the center here. Perhaps you can just make out a small dark bar. What we're looking at, edge on, is an accretion disk. This is all the material is accreting around this star and is producing a prototype solar system. It's a little bit too dusty to see the detail of what's going on in there, but we think this is a very early protostar where the material is being brought in from around many light years away, and this disk here, this tiny proto solar system, is probably larger than our solar system as it stands at the moment. So you can imagine fitting, if our sun was at the center there, all of the planets in our solar system would fall well within the size of this tiny little disk right at the neck of this Hourglass nebula. Again, looking at images like this gives us a better handle on how stars are born. But there are other telescopes coming online. So I've talked about a couple of space telescopes, the Hubble and the James Webb, but here on Earth we have a couple of big telescopes coming our way. One of them is called the Large Synoptic Survey Telescope, or at least that was its original name because it's now been renamed the Chamonix Survey Telescope. But the title, Large Synoptic Survey Telescope, or LSST for short, the LSST is an acronym that's been used so much they decided to keep the acronym even though the telescope has been renamed. So now they're talking about the Legacy Survey of Space and Time, again LSST. This telescope is going to be surveying large chunks of the sky regularly from its base in Chile. How can it survey such a large region of sky? Well, remember the Hubble Space Telescope only images a tiny region of the sky. The Hubble would not be able to survey the whole sky. It would take centuries for it to do so. What you need is a much larger field of view, and the field of view of the LSST, far from being similar to this red rectangle here, the field of view of this telescope is so big I can't even fit it on this particular graphic. It would be a circle that you can see the edge of there. The blue circle indicates the field of view of the LSST camera to the same scale as the HST field of view. So you can see the amount of sky that the LSST will be able to image is vastly bigger than the amount of sky that the HST can see. There's the mirror of the LSST telescope. It's about 8 meters in diameter, and 8 meters is not that large for a Earth-based telescope, but you can see compared to a person it is absolutely huge. And the camera inside, no, that's not it, just for scale, that's the camera that you probably have in your mobile phone. And to give a sense of scale, on the same scale, that's the size of the chip inside the Hubble Space Telescope. So the Hubble Space Telescope main camera chip is about 4 centimeters on a side. It has 16 million pixels and it's about 40 millimeters by 40 millimeters. And perhaps that doesn't sound too great for those of you who've got, for instance, a digital SLR camera. You might well have more than 16 megapixels on the chip in your camera. And the chip is probably not that big, but it's not that much smaller than the sort of chip we're talking about for the Hubble. But the detector on the LSST, because it has a huge field of view and we want to collect lots of data in one exposure, the detector has to be much, much, much bigger than the chip inside the Hubble Space Telescope. So let's just get a feel for how big that is. If that's the 16 megapixel chip in the Hubble, let's add another 8 and make a little block of 9. So this is already 9 times as many pixels as in the Hubble Space Telescope. But let's take that block and let's add another 8 of the same, and then another 12 of the same, and then a few more chips that are responsible for focusing and tracking. That is the size of the detector in the LSST telescope. It is huge. It's the size of a coffee table. Rather than just being a few centimeters on a side, it is 0.6 by 0.6 meters. And this particular detector has more than 3 billion pixels. And the idea is the information we read out very quickly in just a second or two, and it will take exposures something like every 15 seconds. It doesn't need to expose for a long time. It has a nice large mirror, 8 meters in diameter. So it will be able to take relatively short exposures, which means it will be able to take a lot of images in a given night. And each image will comprise more than 3 billion pixels. And it's impossible to show you what sort of image this might produce. This telescope will be coming online in hopefully just a few years, maybe 2024. It's been, like most telescope projects, it's been put back a little bit because of the pandemic. But when it comes online shortly, it's difficult to show you what sort of images it might produce because, of course, my monitor and your screen cannot possibly show you the result of 3 billion pixels. So just to give you a flavour, let me show you what it might produce by showing you what's going on in just a tiny part. Let's just take a small part of the entire detector and show you what it might produce. That's a simulation of what it might gather in a single 15-second exposure. So it's not going to need to image for many minutes or many hours in order to capture the light from thousands of galaxies and tens of thousands of stars. Even in this small little section here, you can get a feel. Remember, this is only 0.03% of the total. The entire thing is some 3,000 times the area you're looking at now. And yet we've caught thousands of stars and galaxies. So that gives you a flavour for what we can expect to get from a single 15-second exposure. And this telescope will be taking pictures all night, essentially every clear night, which is most clear nights because it's being located on the mountain tops of the Andes in Chile. So it'll be taking huge amounts of data and surveying the entire sky over a period of a few nights, and then resurveying to see what is changing in our skies. It will be able to look and catalogue many billions of stars. So this is a schematic of our Milky Way. There's the sun down close to the bottom. We're not going to be able to see every star in the galaxy because some of the stars are obscured by the centre of the galaxy. But we will be able to end up cataloguing many, many billions, tens of billions of stars, as well as billions of more distant galaxies. So the surveying aspect of the Large Synoptic Survey Telescope is critical to actually define what is out there and catalogue as many stars and as many galaxies as possible. In the process, it'll provide data that might help us understand not only the dynamics of the Milky Way, but it might help us understand, for instance, where is all the dark matter? We think dark matter is out there. I gave you a talk about dark matter a couple of years ago. We think this stuff is out there. It doesn't seem to behave like ordinary matter. It's not made of the stuff that stars are made of, or gas or dust. It is something else which we don't understand. And part of the job of the LSST is to try and map out where all this dark matter is and has it changed with time. This is simply an artist's impression showing that maybe dark matter is clumpy, but we don't actually know. This is a superposition of the Andromeda galaxy with a guess as to what the dark matter distribution might be around a galaxy. But as well as the LSST, there are other telescopes coming online. For instance, the European Extremely Large Telescope, the clue is in the name there. You can see that this is an absolute monster compared to other telescopes that either exist now or will exist in the future. To get an idea of scale, the mirror diameter is approximately 40 meters, and it's difficult to get the scale until you look at the people down at the bottom here and you realize just how big this is. Notice also the people on the gantry, again trying to give you a sense of scale. So the main advantage here is to collect as much light as possible so we can see the faintest of objects. The Large Synoptic Survey Telescope will be surveying what's out there, and then it will be telling telescopes like this what to look for. Here's a reminder of the scale that we've been talking about. Grand Telescopio Canarius, yellow at the top, is the largest one to date, and in the bottom right there we have the Extremely Large Telescope. Again, just to try and give you a sense of scale, there's a human, and if that doesn't really help, there's a tennis court in the bottom left and a basketball court in the bottom right to give you an idea of just how large these telescope mirrors are when all of these segments are brought together to make these monster telescope. A 30 metre is planned and the 40 metre is being built. But that's not necessarily the end of the story, because when thinking about large telescopes, people started thinking, well, how big a telescope could you actually make? What is the limit of technology? And some people said, well, is it possible to build a telescope as indicated by the rather grey donut in the background? Let me just highlight in the red so you can see it a little more clearly. Is it possible to build a telescope with a mirror 100 metres in diameter? Well, there was no funding for such a beast, which is why we end up with plans for a 30 metre telescope and the 40 metre Extremely Large Telescope. What would you call such a telescope if it ever existed, 100 metres in diameter? Well, we've already used VLT to stand for the Very Large Telescope, and we've just seen that we use ELT for the Extremely Large Telescope. Are we running out of adjectives? Well, somebody has suggested that maybe this 100 metre diameter telescope ought to be called the OWL, the Overwhelmingly Large Telescope. So, no funds yet, but maybe one day it will happen. So we want to understand the universe, and all of these telescopes will have their part to play if we want to understand what's out there. We need survey telescopes to map out the sky as quickly as possible on a timescale of days to tell us everything that's out there, and then keep looking day after day, week after week, month after month, to tell us not only what's out there in terms of cataloguing billions of stars and galaxies, but tell us how they are changing. And that will inform the objects that we go and have a look at with these large aperture telescopes like the Extremely Large Telescope being built in Chile. The LSST will tell us what to look for, and the ELT will follow them up and look in more detail at specific objects. And we will always need space telescopes lifted above the Earth's atmosphere or sent to the Lagrange Point L2 in order to give us the clearest view possible for a given aperture without the blurring effects of the Earth's atmosphere. All of these telescopes working together will collect enough data to answer some of the questions we have about the universe. But more importantly, they will reveal the questions we haven't even asked yet. Thank you for listening.